Hello, I am Václav Novotný and welcome to the tutorial of energy sources and conversions. This tutorial will be focused on low carbon technologies, renewables and nuclear power. Specifically, we will look at wind power, hydropower as hydro storage power plant and nuclear reactor. So we will start with example calculation of a wind turbine, where the task is to determine amount of work extracted from the wind by wind turbine, where we have the parameters of the rotor diameter and wind speed before the turbine, and we have also given wind speed after the turbine. So 30 meters rotor diameter and wind speed 15 meters per second, and the turbine will, after the turbine, the speed will be 5 meters per second. For this calculation, we will assume efficiency of generator to be 100%. We will neglect any effects of aerodynamic efficiency, of conversion of wind kinetic energy to shaft, and also we will consider things as uniform wind speed across the rotor area. So going for the solution, we can chart an illustration diagram of our problem, where we have the blades of the wind turbine with wind speed in front of it. After the wind turbine, the wind speed is lower, we have certain diameter, and the kinetic energy is converted into shaft energy and then by generator into electricity. So in order to calculate the energy that we get, it's actually a difference in kinetic energy. So if we reference it per unit of mass flow rate, kinetic energy is half of the speed square. Probably you know from the high school the kinetic energy half of the mass times velocity square. So this is per kilogram per second or per kilogram. And so the difference in the kinetic energy is 1/2 multiplied by the kinetic energy before the turbine and kinetic energy after the turbine. So in the numbers, half times 15 meters per second square minus 5 meters per second square, and we get that it's 100 joules per kilogram of the fluid that goes through the rotor. Then we need the rotor area, which is just surface of a circle, and mass flow rate of the air, which is the surface area multiplied by the velocity, where the velocity across the rotor is the velocity before and after divided by 2, and multiplied by the density of the air. So with the numbers, we have the 707 square meters, 1.2 kilograms per cubic meter of air density approximately, and 15 plus 5 divided by 2 average wind speed. So we get the result that per each second through this area would, and with given wind speed, will pass almost 8.5 tons of the air. Now we can get the power output, which is the unit work multiplied by the air mass flow rate, and we will get almost 850 kilowatts. Also we can express the work altogether. So it's 0.25 times surface area density and difference in the squares of the velocity multiplied by the velocity 1 plus the velocity 2, which was before, divided by 2 in the part where we had the mass flow rate. So kinetic energy, mass flow rate, just the 2 went here, so from 0.5 we have 0.25, but you can see that the velocity u1, if we expand this, will be in the cubic, it will be power of 3. So we can see how the power output is very sensitive and rising very sharply with the wind speed. And also we can use this formula and take derivative of it, particularly derivative of power with respect to the wind speed after the turbine, and if we put it equal to 0, so we will get two roots of the resulting equation. One is that the velocity u2 would be minus velocity u1, which is physically not possible, it doesn't make any sense. And the other one is that the velocity u2 would be 1/3 of the velocity of the air, of the wind speed before the wind turbine. So this is the point of the maximum power output, and if we insert this u1 divided by 3 back into the original equation, so we will get something called Betz equation, where the maximum power which can be extracted from the wind is the surface area, density divided by 2, u1 to the power of 3, and 16 over 27, which is roughly 0.59 or 0.6. So we can see that the maximum power or maximum kinetic energy that can be extracted from the air is about 60% if all the other efficiencies are neglected. Now we will move to the example of hydropower plant, where we will consider a specific power plant in Czechia, pumped storage hydro plant called Dlouhé Stráně, where the upper reservoir is at the top of the hill at the elevation 1350 meters above sea level, with about 2.6 million cubic meters of volume. The lower reservoir is in a valley at the height of 825 meters above sea level, and this power plant has two reverse Francis turbines. Reverse means that they can use as turbine in the power plant mode and pumps in the reverse or pumping mode. And for each there is a piping with diameter of 3.6 meters and velocity during discharge of 6.8 meters per second. We will neglect any pressure losses in the pipings and valves. We will neglect changes in the reservoir levels during charging and discharging, and assume turbogenerator efficiency of 94%. And the task is to determine power output and discharging period of this storage power plant. So moving for the solution, the potential energy, the hydropotential, and then actual power output can be obtained as potential energy gravity acceleration multiplied by change in the height. So for the theoretical work, it's the mass flow rate times gravity acceleration and change in the height, and the mass flow rate is volumetric flow rate times density. This was the theoretical potential. The actual power output is of course lower because of some turbine and generator efficiency. So now we can get the volumetric flow rate and then discharging period. That the volumetric flow rate is the area of cross-section area of the pipe multiplied by the velocity. So it's 69 cubic meters per second. And for the discharging period, it's just the volume of the reservoir divided by the volumetric flow rate, and if there are two turbines, both of them in operation, so number of turbines. And we will get that for this case the discharging period from fully charged full upper reservoir, it can run for the full power output over the course of 5 hours. Now from the volumetric flow rate we can get the mass flow rate. just multiply it by density. Here is density for about 20 degrees C. And with the mass flow rate, we can get the theoretical power output, which is 356 megawatts. And then if we multiply it by efficiency, so we will get 334 megawatts per one turbine. And the total power output of this plant would be almost 670 megawatts. Now we have second part of the example where we will have a look at the pumping regime. So in the pumping regime, the power input of single reverse turbo generator is 312 megawatts. We will again neglect any pressure losses or elevation differences, and in the pumping regime the efficiency is typically lower, and specifically at the value of 85%. So to get the mass flow rate, we will use the equation for the hydropotential and express the mass flow rate out of it. So we will get the work of the pump divided by the efficiency of the pump, that is the hydraulic work that is delivered to the working fluid, to the water, and then we have the gravity acceleration and elevation difference. So in the pumping regime, the mass flow rate is 51,500 kilograms per second. Then the volumetric flow rate is just mass flow rate divided by the density, so it's 51.6 cubic meters per second, and we can see again with the same formula as before, the volume of the reservoir that we need to fill divided by the volumetric flow rate and number of pumps. We will get the period of charging, period of pumping, 25,000 seconds, which is almost 7 hours. And the last and probably most important is the round-trip efficiency of this system. So the round-trip efficiency is the work that we get out of the storage plant divided by the work input into the storage plant. It's work, not the power input. So it's in joules or megajoules, kilowatt hours, megawatt hours, these units, not in kilowatts. We can also express this round-trip efficiency with the power, but multiplied by the period of charging and discharging, so that we get the energy. So the power output during discharging times the discharging period divided by the power input during charging and the charging period. And also we can express it with referenced energy of the energy in the storage. So the discharging power, the discharged energy can be expressed as the energy stored multiplied by the efficiency of the discharging process, and the energy input as energy stored now divided by the efficiency of the charging process. So this stored energy is in both. So this stored energy can be cancelled out, and we will get efficiency of the turbine multiplied by the efficiency of the pump, or efficiency of the discharging process multiplied by the efficiency of the charging process. So it's 94 times 85%, which is 80% of the round-trip efficiency, how much electricity we get compared to how much electricity we put into the storage system. The last example for today is nuclear reactor, where we are asking how much fuel needs to be annually changed for 1000 megawatts of electricity power plant, which is something like single block, single reactor unit of Temelin nuclear power plant. So we will assume that the fresh fuel is enriched for 4 mass% of uranium-235, and the spent fuel has content of this uranium-235 of 0.4%. For this calculation, we will assume that the heat originates only from fission of uranium-235 and all of it is utilized. In real life, some of the energy is taken away by neutrinos, and you also get a little bit of energy by radioactive decay of the fission products. But both are relatively small values, both the extra energy from the fission products and the energy taken away by neutrinos. For the power plant, we will assume conversion efficiency of heat to electricity as 30%, and that the power plant is running on nominal power output for 7,000 hours a year out of 8,760 hours, which is the optimal regime for nuclear power plants. So now going for the solution. First, we will get the heat input required throughout the year. So heat input for the plant running for 7,000 hours is the electrical work divided by the efficiency of conversion multiplied by the period of operation. So we get 8.4 times 10 to the power of 16 joules per year. And now we continue with the nuclear reaction, where energy per single fission is the 200 mega electron volts multiplied by 1.6 times 10 to the power of minus 19 joules per electron volt, which is 3.2 times 10 to the minus 11 joules obtained, joules of energy, joules of heat obtained per single fission of uranium-235. Now when we have these two values, we can get the number of required fissions per year. So it's the heat which is required divided by the energy of single fission, and we get 2.6 times 10 to the power of 27 fissions in 1 year to get the required energy. And now we can get weight of a single atom, that is molar weight of the uranium-235, which is 235 kilograms per kilomole, divided by the Avogadro constant, which is 3.9 times 10 to the minus 25 kilograms. So now we have number of fissions, we have weight of single atom, so we get mass of the uranium-235 that we need in a year, and we need them to perform the fission. So it's number of fissions multiplied by the mass of the single atom, which is 1023 kilograms a year. So it's actually quite small amount of the fuel compared to, for example, coal power plants that are consuming values like this within an hour or even faster in the coal. So now we can continue with the mass of uranium fuel, which is the uranium-235 plus ballast uranium-238. So it's the annual required amount of the uranium-235 which performs the fission, divided by the difference in the concentration of the fission material of the U-35. So it's 28.4 tons per year. And now we can also get the values for the uranium fuel ceramic fuel UO2. So the average molar weight is the 1/7 sum of concentrations divided by molar weight of each component. So we have the concentration 4% of uranium-235 and remaining 96% of uranium-238. And then the molar weight of the UO2 of the ceramic fuel is the molar weight of the uranium fuel plus the molar weight of O2, because we have molecules UO2. So it would be almost 270 kilograms per kilomole. And now we can use this to get the mass of the ceramic fuel per year, which is the required mass of the uranium fuel multiplied by the ratio of molar weight of the ceramic fuel over just the fuel contents of the uranium isotopes. So we get 32 tons per year. And now what does it mean? These huge amounts of fuel, which are also similar values, would be those huge amounts of the nuclear waste. So how much of the fuel or waste actually is with respect to volume? So we have the required mass of the uranium multiplied by the uranium UO2 fuel multiplied by its density. So we can see that it's 3.1 cubic meters of the fuel per year, or also approximately 3.1 cubic meter of the radioactive toxic uranium waste a year. This huge amount of the waste can be actually fitted into 3 regular trash containers, if we look at it like this. So instead of looking at it like a huge amount of waste, it is actually a very small amount of waste that can be easily contained compared to, for example, all the emissions that exit through the stack in fossil fuel plants, or all amounts of the electronic waste and other waste from manufacturing solar plants or wind turbines. So this is all for this tutorial.